As 3I's Atlas descends toward its closest pass by the Sun, instruments built to study solar storms begin whispering about something else entirely. Magnetometers aboard Solar Orbiter and NASA's Parker Solar Probe detect a subtle rhythm in the solar wind, pulses that appear to move in lockstep with the interstellar visitor itself. The readings are faint but steady, rising from background noise like a hidden heartbeat. At first, analysts at the Heliophysics Science Division suspect interference, perhaps a calibration echo or solar particle drift. But hour after hour, the signal refuses to fade. Separate spacecraft, separated by millions of kilometers, all record the same pattern. Rotating, repeating, and impossibly aligned with 3I Atlas's predicted path. By midnight, what began as a statistical anomaly becomes a confirmed enigma, a coherent magnetic pulse where none should exist. If real, it would mark the first time any interstellar body has shown evidence of magnetic structure inside the heliosphere. And so, a single question spreads from lab to lab, mission to mission. How could a frozen traveler from another star carry a field of its own? The first alert came from ESA's Solar Orbiter during its inbound leg on November 8, 2025. Magnetometer specialists noticed a faint but repeating oscillation in the interplanetary magnetic field, a wave-like distortion rising above the background turbulence of the solar wind. At first, it seemed insignificant, a numerical quirk lost in plasma noise. But the periodicity was unusual. The waveform held a steady rhythm, fluctuating every few hours, its vector gradually shifting eastward. Hours later, NASA's Parker Solar Probe, operating millions of kilometers closer to the Sun, reported a near-identical anomaly. The Stereo A spacecraft, trailing Earth's orbit, captured the same signature from a completely different vantage point. 3 independent platforms, 3 separate instruments, all detecting synchronized field oscillations along the predicted path of 3I Atlas as it approached perihelion. By evening, the Heliophysics Science Division issued a Level 2 anomaly report citing localized field coherence inconsistent with solar origin phenomena. Time-stamped logs from both Parker and Solar Orbiter showed the distortion moving with the object's predicted motion vector, rotating slightly as if carried by something solid. Analysts ran comparison models using the CCMC's solar wind database, subtracting expected turbulence from flare activity. The pattern remained. The conclusion was cautious but direct. The disturbance was real, spatially constrained, and correlated with 3I Atlas's transit. A body that should have been magnetically inert appeared to be influencing the field around it, and that raised a deeper question. How could a fragment of interstellar ice produce a signal magnetic enough to be heard across the Sun's domain? Under normal conditions, the region of space now hosting 3I's Atlas is dominated by the Parker spiral, a steady corkscrew of solar magnetic flux carried outward by plasma flow. This spiral forms the backbone of the Sun's magnetic influence, its invisible structure guiding charged particles through interplanetary space. Every probe and solar model depends on its predictability. For decades, no spacecraft has recorded a deviation large enough to suggest a localized disturbance. Until now, the spiral itself appeared unbreakable. During solar maximum, this zone becomes turbulent with transient kinks and folds, but the overall structure remains smooth, an unbroken field extending from the Sun's surface to beyond Mars. Instruments such as the Wilcox Solar Observatory and NASA's Community Coordinated Modeling Center, CCMC, simulate this field daily, predicting minor polarity shifts tied to solar wind velocity. In all of these models, there should be no self-contained magnetic islands, no rotating field bubbles unrelated to solar origin. The November readings did not fit that pattern. When analysts plotted the data, the local field vector reversed polarity every 8.3 hours, an impossible rate for standard heliospheric rotation. Even stranger, the magnitude of the reversal decayed with distance from 3I Atlas's predicted line of motion, suggesting a localized moving source. Cross-correlation with solar flare logs showed no eruptive events capable of producing that shape. No coronal mass ejections, no high-speed streams. The anomaly's waveform exhibited coherence, a repeating signal structured and consistent, superimposed upon the chaotic solar background. In theoretical terms, the disturbance behaved like a weak dipole rotating through space as if anchored to a central mass. But interstellar bodies, especially small ones, should carry no active magnetosphere at all. Something inside 3I Atlas, or interacting with it, was shaping a magnetic field where none should exist. Confirmation came within 48 hours. The Deep Space Climate Observatory, DSCOVR, at the L1 point detected a matching pulse, a faint rise in magnetic intensity occurring precisely as Solar Orbiter recorded its second rotation cycle. At nearly the same time, Japan's Hinode spacecraft, equipped with its solar optical telescope and vector magnetograph, logged concurrent distortions in the surrounding solar plasma, mirroring the oscillation pattern. Data teams in the Heliophysics Science Division initiated an emergency cross-calibration campaign, drawing inputs from 6 spacecraft and multiple ground stations. Using real-time magnetohydrodynamic (MHD) simulations, analysts ruled out interference from coronal mass ejections or solar wind compression fronts. Each potential solar explanation failed. The timing, direction, and rotational periodicity remained bound to 3I Atlas's modeled coordinates. At Imperial College London, researchers plotted all readings against the predicted light curve derived from JWST photometry. 2. Their astonishment, the field fluctuation matched the previously observed 8.3-hour rotational period, a perfect synchronization between light variation and magnetic modulation. That alignment was too precise to ignore. Peer verification followed rapidly. NOAA's Space Weather Prediction Center, ESA's ESOC, and JHU Applied Physics Lab all repeated the analysis independently, confirming the same cycle and phase lock. The magnetic pattern was real, repeatable, and consistent across instruments and hemispheres. If the correlation held, then 3Psi Atlas was not simply moving through the Sun's magnetic field, it was carrying one. The question emerging in every report was the same. Is the field following the object itself? The first task for heliophysicists was to strip the mystery down to physics. If 3I Atlas appeared magnetic, perhaps the field was not its own but the product of its interaction with the solar wind. The Rosetta mission had already shown how a comet such as 67P Churyumov-Gerasimenko could create a thin, induced field by ionizing gas in its coma. Similar processes were observed around 2I Borisov, where charged dust and plasma currents produced weak, transient signatures. Teams at the Comet Interstellar Consortium modeled whether the same mechanism could explain the readings from 3I Atlas. In those models, solar wind ions striking a conductive surface can generate small electric currents that in turn create secondary magnetic loops. Yet even under extreme assumptions, high metallicity, dense plasma flux, and rapid rotation, the induced field strength barely reached 1/10 of what Parker Solar Probe had recorded. The coherence of the signal also defied expectations. Normal cometary induction collapses within minutes as plasma density fluctuates, but the 3I Atlas pattern persisted for hours, steady through multiple rotations. Thermodynamic simulations showed that maintaining such a field would require current densities orders of magnitude higher than solar ion pickup could produce at 1 astronomical unit. In short, known natural induction could not sustain a coherent dipole field of this duration or strength. As one researcher summarized in a preliminary report, if this is an induced field, it is behaving as though the generator is on the object itself. At this stage, discussion shifted from explanation to hypothesis. The working idea, still unconfirmed, is that 3I Atlas might possess a metal-rich or magnetized core capable of generating its own transient magnetic field. This would not be a planetary-scale dynamo, but a weak, self-contained magnetization sustained through rotation or internal stress. Researchers at Imperial College London and the Johns Hopkins Applied Physics Laboratory have explored how remanent magnetism could survive inside differentiated interstellar fragments. Laboratory experiments on iron-nickel meteorites show that crystalline structures formed in cold interstellar environments can retain residual magnetization for millions of years. If 3I Atlas contains such materials, rotational friction or tidal flexing could re-energize those fields temporarily, producing the small, repeating dipole signatures observed. Another speculative model involves piezoelectric effects, electric potentials generated as a rotating body undergoes stress cycles. Though largely theoretical at this scale, simulations suggest that in a metallic silicate matrix, even minor deformation could create charge separation strong enough to perturb nearby plasma. These mechanisms remain hypotheses, not proven sources. No direct measurement confirms the presence of a core or magnetic minerals, but the data fit the pattern. A weak, structured field that rotates with the object rather than the sun. If future spectra verify metallic components within the nucleus, the case for a self-generated field will strengthen. For now, the question stands on the threshold between possible and extraordinary. As magnetometer data accumulated, optical and radio instruments joined the investigation. The James Webb Space Telescope's NIR SPEC unit captured near-infrared spectra during late October, while the Atacama Large Millimeter-Sub-Millimeter Array, ALMA, conducted follow-up polarimetry from Chile. Both datasets revealed faint but measurable circular polarization in the light scattered from dust surrounding 3I Atlas. Circular polarization often indicates magnetic alignment in micron-sized grains, tiny compass needles responding to an external or local field. When researchers compared the polarization vectors to the object's rotational phase, the alignment rotated in step with the 8.3-hour period recorded by solar orbiter's magnetometers. Statistical analysis showed a phase lag of less than 5 degrees, essentially synchronous motion. Alternate explanations were examined first. Calibration errors could have produced false polarization, so could forward scattered sunlight or instrument diffraction. Yet when independent teams reprocessed the raw data, the pattern remained. Even ALMA's radio band detections, operating at completely different wavelengths, showed the same handedness reversal over the same cycle. If these correlations hold, the simplest explanation is that the dust grains are aligning within a weak magnetic field that co-rotates with the nucleus. The phenomenon has been seen in active comets, but never with such persistence or precision, and certainly not in an interstellar body. The implication is startling. If the polarization follows the object, then so might its field. Within days of the magnetometer findings, official channels lit up. The International Astronomical Union issued an electronic telegram citing unusual magnetohydrodynamic activity, coincident with the trajectory of 3I Atlas. The Minor Planet Center followed with 2 circulars updating positional data and urging coordinated monitoring across heliophysics missions. A joint NASA-ISA press release described the phenomenon as a structured magnetic disturbance requiring further investigation, careful not to suggest any intrinsic field. In press briefings, Dr. Nicola Fox, NASA's Associate Administrator for the Science Mission Directorate, emphasized restraint. Correlation is not confirmation. These data are valuable, but they remain preliminary. At ESA headquarters, Daniel Miller, project scientist for Solar Orbiter, echoed that tone, noting that the instruments were designed for solar physics, not magnetometry of transient interstellar objects. Behind the scenes, debate intensified. Some plasma physicists argued the pattern reflected a solar wind boundary effect, a magnetic echo caused by turbulence near perihelion. Others urged direct reobservation, pointing to the consistent 8.3-hour phase lock as impossible to dismiss as noise. Access to the raw magnetometer archives was briefly embargoed while calibration audits were conducted, sparking friction within the research community. Calls for transparency grew louder as independent analysts demanded open data to replicate results. For now, the consensus remains cautious but captivated. 3I Atlas has provoked one of the most complex cross-agency debates in recent heliophysics memory. The next window to test the magnetic field hypothesis opens in December 2025 when 3I Atlas moves back into observational range. A coordinated campaign will merge instruments across 3 major missions. Parker Solar Probe, during its 19th perihelion, will attempt to sample the solar wind downstream of the object's projected path, looking for periodic field modulations. Solar Orbiter, positioned at a complementary angle, will remeasure magnetic flux density along the same vector using high cadence mode. In parallel, JWST's NIR spec will re-examine spectral and polarization features to confirm whether the circular polarization detected earlier persists. Ground-based efforts include the Vera C. Rubin Observatory, set to perform continuous photometric sweeps for correlated light curve oscillations, and ALMA, which will repeat its polarization mapping. Together, these data could establish whether the field co-rotates, dissipates, or shifts independently of solar wind vectors. Each dataset holds a distinct diagnostic. If the magnetic signature fades as the object recedes from the Sun, interaction models gain strength. If it remains stable or strengthens, the self-magnetism hypothesis will demand serious reconsideration. The first consolidated data dump is scheduled for late January 2026. Scientists anticipate it could either close the case or rewrite the understanding of magnetic behavior in interstellar matter. As one JPL engineer remarked, "Whatever it is, we will soon know if the field belongs to the Sun or to the visitor itself." After months of analysis, 3 results are beyond dispute. First, multiple spacecraft independently detected magnetic fluctuations aligned with the trajectory of 3I Atlas. Second, those oscillations repeat every 8.3 hours, matching the object's known rotational period. Third, no solar or instrumental source fully accounts for the coherence or timing of the signal. Beyond these facts lies only hypothesis. The idea of a self-generated magnetic field remains unproven, yet physically plausible if the nucleus contains metallic or magnetized components. Upcoming data from Parker, Solar Orbiter, and JWST will decide whether the field is intrinsic or induced. The implications are far-reaching. A verified magnetic field would suggest that interstellar bodies can preserve or regenerate magnetism across light years, implying a complexity of structure previously reserved for planets and moons. It would mean that even solitary fragments drifting between stars might carry traces of internal order, records of the environments where they formed. For now, 3I Atlas remains silent, its signature buried in solar interference until December's reappearance. Researchers prepare, calibrate, and wait. The data will tell whether the signal was a solar echo or something generated from within. Until then, one question defines the mystery. Is 3I Atlas merely reacting to the sun or carrying a magnetic heart across the stars?